Okay, well, thanks very much, and it's great to be here, and glad so many people could make it, and thank you, Schengen, for that great introduction, too. I do want to start by, again, drawing attention to the list of authors. This was very much a team effort with tremendous inputs from all listed there, and many of them are here in the audience, so thanks to all of them as well. Is this going to work here? What's the forward? Green. I gotcha. So first, I'm going to start just with a quick project overview. As Schengen's already said, there's a number of drivers out there that we think is leading to a structural change in future prospects for supply, demand, and prices globally. Some of the key ones I already mentioned is climate change, water scarcity, continued biofuel demand, and other demands for food production being diverted from food to other uses. And we're also seeing, of course, long-term income growth. A key new factor in the equation is that income has now begun to grow much more rapidly in Africa. And there we see very high propensities to consume food out of that increase in income. So that's going to be another shift upward in long-term demand. Population growth continues to be strong. We're expecting to go up from about 7.2 billion now to about 9 billion in 2050. And then our IFPRI projections out to 2050 and a baseline scenario that includes climate change, which is also the baseline we compare technologies to in this particular study. We do project higher long-term prices for all the key staples, rice, maize, and wheat, also soybeans and livestock as well. So unless a lot better progress is made on agriculture productivity growth, we do see continued long-term problems in terms of food security for the poor due to high and rising food prices. We see, of course, growing threats to land and environmental preservation, water quality, as well as quantity, and biodiversity as well. So there's also significant ecological threats depending on how we grow more food as well. We think, and in fact, Schengen also already mentioned that enhanced investment in agriculture research and technological change has been a game changer in the past, and we think it can be in the future as well. There's a lot of understanding that on a broad basis, agriculture research and development has very large impacts on production, very high rates of return, as Schengen also noted. But in general, we haven't seen enough work that disaggregates the impacts of specific technologies by country and region and agroclimatic zone. And that's what we really attempt to do here to add additional knowledge to the assessment. So what we're doing, we'll present here a global and regional perspective, just skimming off some of the key results as we go through. We look at a total of 11 technologies that are listed there, and I'll run through them in a moment with just very brief capsule descriptions. As you can see, they include farming systems such as no-till, integrated soil fertility management, organic agriculture, and precision agriculture, and crop protection, and then higher technologies such as drip irrigation and sprinkler irrigation. Also, water harvesting is assessed. Then we also look at technological change through enhanced seed varieties that encompass drought tolerance, heat tolerance, and nitrogen use efficiency. And here we do focus on wheat, rice, and maize. Just briefly, just to put people on the same page in terms of the technologies that we're looking at. So just no-till, of course, is minimum or no soil disturbance, and no more plowing soil up and under, and often combined with management systems to retain residues, and also crop rotation and use of cover crops to try to increase the long-term organic matter and fertility of soils. Integrated soil fertility management uses a combination of inputs, including crop residues, manure, and compost, in addition to additions of chemical fertilizer to get sort of broader-based nutrition. Precision agriculture, which we also look at, it includes like GPS-assisted delivery of agriculture inputs, as well as other localized management practices to aim to control field parameters and apply inputs in a very highly efficient way, targeted to exactly where they're needed on the field, like fertilizer and water, for example. Of course, organic agriculture is cultivation with strict limits on use of manufactured fertilizers, pesticide, and GMOs. Water harvesting is where there's usually we're thinking of localized catchments that capture rainwater and then can be used to apply to water more to fields more efficiently. Drip irrigation is directly applied water often through microtubing or pipes directly to each plant or the root zone. And sprinkler irrigation then, of course, distributes water through pipe networks and delivered to the crop via sprinklers. Heat tolerance, here we're looking specifically at improved varieties that have characteristics that allow plants to maintain or even increase yields at higher temperatures. Drought tolerance, of course, is to allow improved yields or sustained yields even under drought conditions. The nitrogen use efficiency is breeding, of course, of varieties that respond better to fertilizer, so you can either get more output for each unit of fertilizer or reduce the amount of fertilizer to get the same output. And crop protection, of course, is managing pests, plant diseases, weeds, and other organisms. So to look at these technologies, we do a two-step linked approach. The first is using the DSSAT models. These are biophysical models of crop production, highly detailed, that assesses the impact of any single technology or technology mix. And here we can look at productivity or crop yields per hectare, which is what we use in most cases here. But it also allows at least some assessment of resource uses, and particularly water use and nitrogen usage and losses. We then link the results from the DSSAT model, and I'll say a bit more about that in a moment, to the IFPRI's global economic agriculture model called the impact model, which assesses long-term changes in productivity due to technology adoption, but incorporating also the impacts of markets and policies. And here we look then at the outcomes on food production, consumption, trade, food prices, and calorie availability, and food security as well as a result of the technologies that we model. We have a high resolution of analysis for a global model. It's a 0.5 degree grid level assessment, which is equivalent to 60 kilometers by 60 kilometers. That yields almost 100,000 cells globally, of which over 21,000 have cover cropland extent for these three crops. So we're actually analyzing through the DSSAT model the production outcomes due to the technologies at that level of detail. We do a number of scenarios for the assessment. Overall, the business as usual scenario, which I mentioned, incorporates essentially the current technologies with some improvements over time, but not the kinds of improvements that we assess in their technology scenarios. We then look at specific representations of the technologies for the technology scenarios and compare, in most cases, we compare what happens in 2050 with the technologies to 2050 without the technologies. We also use two different climate change scenarios based on two global circulation models. That's the Meroc A1B and the CSIRO A1B scenario. And we used a two to make sure we're not just picking one climate change model that might skew the results. And these two models represent sort of relatively positive, relatively negative outcomes on this A1B scenario. But the scenario in general does have about a 2 to 2.5 degree increase in temperatures between 2000 and 2050. So significant, but not as bad as some of the climate change predictions we're seeing now. So how do we do these specifications? I don't have time to show all of them, of course, but I want to show an example, and this is for drought tolerance. So we simulate this with three different interventions within the crop models. One is the increased root volume, which is implemented by increasing root growth factor parameters in the model, enhanced root water extraction capability, so we decrease the lower limit of available soil moisture parameters to allow them to access additional soil moisture and then for maize, we also were able to incorporate one of the key mechanisms identified, which is less sensitivity to the anthesis or flowering to silking interval, which is a key growth period. So that we implemented by modifying existing models to have differential ASI as a cultivar trait So by doing this, we're capturing some of the key parameters of drought tolerance. And we also then implement each of the other technologies. So again, DSAT is first use. We look at the technology strategies, which technology is available. Then we estimate the corresponding geographically differentiated yield effects out to 2050. We plug in those yield effects, the biophysical yield effects, into the economic model, which then can also estimate food demand and supply, effects on world food prices and trade, and food security and malnutrition. So let's now get into the results real quickly. So we'll start here showing the results for the biophysical potential. These are the global results for DSAT, for maize, wheat, and rice. Again, this is projected out to 2050 under adoption of the technology as specified there compared to the baseline without that adoption. Let me just run through some of the key results. Drought tolerance on average, as you see there, is relatively modest, but the thing to point out is that that's averaged across all water outcomes out to 2050. So in a large number of the years, there's no water, there's no drought at all. So this is actually a positive effect in that we're seeing that even on average, drought-tolerant crops can outperform the non-drought tolerant crops. There's been debate in the past whether that's true or whether you'd actually pay a yield penalty on average from drought tolerance. When we've also done other supporting simulations where reduced under drought stress conditions, we can get as much as 20 to 25% improvements in yields due to drought tolerance. Heat tolerance, as you can see, comes off as a very powerful technology, and that, of course, is the potential of that technology is enhanced by the fact that we're in a climate change situation, so the stresses are becoming higher over time. Integrated soil fertility management, nitrogen use efficiency, and no-till, some of those kinds of farming system level technologies have very important positive effects, as you can see. Precision agriculture also comes off very positive. I think some people have been surprised by these results, but we're already seeing, for example, places like India and parts of China where precision agriculture is being adopted. People in the past have said, well, it's decades away in developing countries. That's not true, and I think these results show that, in fact, if that adoption speeds up, there's significant benefits to that. The water scenarios, water harvesting, drip, and sprinkler irrigation, do not come out as large positives on yields, but as we'll see later, that's because the main effect of those is through improving water use efficiency and reducing water use consumption at the local level. Organic agriculture basically has a yield penalty in the analysis we've done, so there's no positive effect at all. It runs negative, but since we only look at the pixels in which there's potential positive effects, that comes out as a 0 here. Then the 3 crop protection results show, again, very strong, solid benefits to crop protection for diseases, insects, and weeds. And if in areas where you would have applications to counteract more than one of these, of course, you then get even higher returns to that. Let me just look quickly at a couple of the regional results that give a little flavor of that. And one thing that we can see that, and here let's look at nitrogen use efficiency, ISFM, and no-till. And I think one key thing that is, in most cases, is the regions in Africa have the highest percentage improvements due to adoption of these technologies. And I think that makes sense in the context that they're starting from a relatively low base, and therefore the adoption of these technologies has significant potentials to boost yields. And I think that's a very, I think, promising effect of that. Parts of Asia also, West Asia, for example, is also very high. But even like in North America, for example, you see that no-till could improve maize yields by about 20% if it's maintained over the long term that we look at. In terms of drought tolerance, heat tolerance, and crop protection, just a few more examples for maize. We don't have time to look through all the other crops. Here you see that tremendous impact of heat tolerance, but also taken down now to the regional level. And again, you're seeing very substantial impacts in places like Central Asia, East Asia, and South Asia, where there's long-term projections of significant increases in temperature. Also, many of the African countries do well. In this case, also, it's, I think, worth noting that the impacts in North America are very high for heat tolerance. And that's partly a function of the fact that the Morocco model that we're using here shows really large negative impact on the U.S. Corn Belt, as much as 30 to 35% losses due to climate change in that region. So the heat tolerance effect that you see here is due a significant part an offsetting of that highly negative climate change impact. In terms of use of resources, here we're looking at changes in nitrogen productivity, again now for the three crops, maize, rice, and wheat, and irrigated and rain-fed conditions. Again, comparing 2050 versus the baseline, and looking here at the nitrogen use efficiency breeding for new crop varieties that are nitrogen efficient, and no-till technologies as well. So you can see that these technologies have strong beneficial effects on reducing the use of nitrogen and increasing the nitrogen productivity in fields. For example, the no-till case there for irrigated areas for wheat that's shown, you're showing almost 30% less irrigation, a reduction in nitrogen losses, and about 28% increases in productivity therefore. So this has, of course, a number of positive effects. Not only you're using less nitrogen, you're reducing the emissions of nitrous oxide, greenhouse gas emissions, so reducing some of the pressure on climate change, and also reducing the runoff of nitrogen that causes pollution and negative effects. We also looked then at the use of the irrigation and the drip and sprinkler irrigation, and examine how they affect the water use applied and the water productivity at the field level or the pixel level here in this case, of course. And here you see a range of results. The drip has a more powerful effect than sprinkler, but sprinkler also generates significant water savings at that location. And some of the benefit of that, of course, is that water can then be used elsewhere in a river basin, for example, either for other crop production or for non-agriculture priority uses, drinking water or services or industry as well. So again, we're seeing significant efficiency gains in the use of resources. Next, we saw these potential results from the biophysical modeling. You know, what is the local impacts on crop yields. Then we feed those into the impact model to see the effects on total crop production out to 2050 under feasible adoption pathways for these technologies. As you can see here, again, we're looking at the three crops, and as would be expected from some of the results I showed, nitrogen use efficiency and no-till have the biggest individual impacts on the total crop production by 2050 in the economic model, but also, again, precision agriculture, heat tolerance, integrated soil fertility management are also substantially high, and the crop protection results also are very substantial, especially if they're combined in certain areas. So the results for the biophysical potential does carry through to significant increases in production in 2050, even in the economic model. Those increases in production, in turn, result in reductions in world food prices. As you recall, I started out by noting that we project significant increases in food prices in the coming decades under the baseline. This shows that even at an individual basis, several of these technologies have very significant impacts on helping to reduce prices. Here for maize, for example, again, we see no-till, nitrogen use efficiency, and drought tolerance also having very significant negative impacts on prices. And here's looking at the same kind of results for rice as well. Again, nitrogen use efficiency comes out very strong here, and you can see the ranking of the others as well. So again, even on an individual basis, these have strong impacts. But of course, none of them alone is going to be completely, is going to solve the issue. Here we see also for wheat, again, and for wheat, no-till has a very large impacts as well as heat tolerance, and you can see, again, the other results. But what happens, so we saw there are powerful individual impacts, but as you can see, looking at those slides, you're not really going to get, you're not going to solve the world food problem or even the supply side of the world food problem through those individual technologies alone. But here's where we look at what would be the combined effects if those technologies were adopted on their feasible adoption pathways to 2050 across the different technologies. And here you see now where you get really substantial improvements for poor people with reductions in prices in the neighborhood of between 40 and 50% in 2050 compared to the baseline case. And this is, of course, particularly important for poor people in developing countries who spend as much as 50% or more of their income on staple foods, that if you get this kind of reduction in prices compared to the baseline, you're essentially increasing their effective income as well as reducing prices. And that in turn results in increased consumption of staple foods. Here also is another of the resource use effects that we wanted to highlight, that when you adopt all of these technologies on their feasible pathways, you also get a very significant reduction in the amount of crop area harvested for these three crops out to 2050, as much as over 20% for maize and wheat and over 10% for rice. That's because the much greater productivity growth under technology scenarios means you can use much less land to get the necessary production that is needed to meet food demand. So again, you're saving land, fallow land or forest land from being converted to cropland. So another very positive environmental effect as well. Then we look at the change in the population at risk of hunger. Again, looking first at the different technologies individually. In this assessment, we use the same definitions as FAO. So this is the number you see often quoted as the number of hungry people in the world. And here again, we see that individual technologies do have strong negative effects, as much as 12% reduction. Shangan mentioned that already on nitrogen use efficiency, no-till, heat tolerance, precision agriculture, and on down the list. Also, individually can help reduce the percentage of population at risk. And overall, if we look at the totals, the reduction in hunger can be 37% when you combine the technologies. So a very substantial benefit from the technologies if we can get broad-based adoption. So let me wrap up with a few of the key messages here. As I noted, adoption of this set of technologies can significantly reduce projected food prices compared to the climate change baseline. We also did a brief assessment that for those farmers who adopt technologies, they can still also increase real incomes because technological change is faster than price decline. Non-adopters would have to make other adjustments. That's one possible issue that's raised. And the number of people at risk of hunger could be reduced. It says 40%, 37% is the number simulated compared to the baseline with the combination of technologies. And we're also seeing that improved land management techniques, including no-till, precision agriculture, integrated soil fertility management, does result in large yield impacts in many of the regions. So those come out as some of the key technologies. If we can get effective nitrogen use efficiency bred into new varieties, that has both strong yield impacts and also reduces negative environmental impacts that can come from high levels of fertilization. Heat-tolerant varieties, as we saw, reduce projected negative impacts of climate change and can have very large overall impacts. Drought-tolerant varieties, as I noted, perform as well as susceptible varieties under drought stress, but also have significant yield benefits under drought conditions. Crop protection, as we saw, for all three types, have strong positive yield effects. And one thing noted, it doesn't come out directly in the slides I showed, but in each of these technologies, the tendency is that the impacts are higher under irrigated conditions. So not just the drip and sprinkler irrigation, but even under current furrow or flood irrigation, the technology impacts, for example, of nitrogen use efficiency are higher under those irrigated conditions because of the greater control of water there. you saw also the large regional differences in agriculture technology impacts, and I think that's will be very helpful in helping to target specific investments or additional analysis of technologies for specific regions. For example, we saw heat tolerance with major impacts in North America and South Asia, drought tolerance in Latin America and the Caribbean, Middle East and North Africa and Sub-Saharan Africa, and crop protection in Sub-Saharan Africa, South Asia, and also in Eastern Europe as well. Organic agriculture in the analysis here, and also is not a preferred strategy for these three crops on a broad base. There is a yield penalty in most cases from agriculture for these crops, but of course it does still have a role in niche markets, and not only in the developed world, but in higher valued markets in developing countries for these, to some extent for these three crops, but also more so for things like fruit and vegetables, in for example, peri-urban areas in the developing world. The other final point that I wanted to make is, again, that given the growing natural resource scarcity, the technologies that also reduce resource use are extremely important. Some of the key ones, again, are no-till, integrated soil fertility management, nitrogen use efficiency, precision agriculture, and drip and sprinkler irrigation, but also to note that of course, that the higher productivity in all of these technologies also helps reduce land use over time. So again, just to a quick sum up, we found strong positive food security impacts for these technologies studied, but getting these technologies to farmers is going to be difficult, and we can discuss more in the discussion period about how we can go about doing this. But it's clear they have to act quickly, really act now, because the cost of inaction, we think, could be dramatically negative for world's food insecure and for our planet's future. And let me just thank also the funding sources for this work, including CropLife International, the U.S. State Department, and the CGIAR research program on policies, institutions, and markets. And we also had a great study advisory panel. Eliseo Continue of that panel is here today, and we want to thank them as well. So thanks very much.
Am I on here? I'll let you make your way back to your seat there, and before we call up Guillaume, there's one thing I'd just like to draw you out on a little bit for a moment. As you were going through these results, you said that some were surprised by some of the results, and I'm wondering where the surprise factor was for others or for you, as a matter of fact.
Yeah, I think one of the ones that came out very strongly was no-till, and I think the issue there is that what we've modeled is that farmers to get these kinds of long-term benefits, they really have to stick to it over many years out through it. So if we model it sequentially, the yield impacts in the early years of adoption are relatively small, but then increase significantly. So if it can be maintained and get the soil health benefits over time, you get significant productivity. Because that's a tricky issue, because if farmers don't see the impacts right away, they may abandon it. So that's one area where a sort of a very important sort of extension and information campaign would be needed to help get the adoption rates needed.
And in the breakdown, you did technology breakdown, you did regional breakdown. Did you do sort of obstacle breakdown? I mean, where no-till, for example, is a harder sell in certain regions than others?
Yeah, we didn't do that in this particular, and I think that's subsequent work that needs to be done to tease out from the results we see and compare to the constraints, physical and economic constraints in the region, to look more carefully at the policies needed to drive the adoption.
Great.